All right, so welcome to the recitation. So we got like half hour. Let's just go through what's going to be on the test. All right, so the magnetism. You can map out the magnetic field using a compass. Compass is a magnet on a pivot. So magnetic field lines will start at the north pole of a magnet, and they will end on the south pole of a magnet. And we know this how? Because the compass always points in the direction of the magnetic field. Earth's magnetic field points to the north. So this implies that there is an invisible magnet within, and it's oriented in this fashion. So the question is, what causes the Earth's magnetic field? All right, so mathematically, this symbol we use for the magnetic field is B. Proper units is going to be Tesla. And in terms of the Earth's magnetic field, once again, it's almost like there's an invisible magnet, and it orients itself in this fashion. All right, so the North Pole is pointing to the south, and the magnetic field lines start at the North Pole of a magnet, and they will end at the South Pole of a magnet. When you take a magnet and break it into smaller and smaller pieces, trying to identify a magnetic north or a south, you will not succeed. It doesn't matter how small the pieces are, it's always going to have two poles. It looks as if the magnetic field is going right through the magnet itself. All right, so the stuff that we already know, the like poles will repel, the unlike poles will attract each other. All right, so the question becomes, what happens to the charges inside magnetic fields? All right, so physicists decided to conduct experiments to figure this out, and here's what they found out. If you place a charge in a constant magnetic field, if the charge is static, nothing happens. If it's moving parallel to the magnetic field, nothing happens. Only if it's going across the magnetic field, it's going to get deflected by a force, which is 90 degrees to its motion. All right, so this becomes the magnetic force. So the static charges will not experience any sort of magnetic effects. If the charge is moving parallel to the magnetic field, once again, nothing happens. If the charge is moving across the magnetic field, it's going to get deflected at an angle, which is 90 degrees to its motion. So this particle is moving from left to right, or from in this direction, not from left to right, but it's moving left to right. So direction of that force is determined by using the right-hand rule. The right-hand rule is going to be used for only positive charges. If the charge is negative, use your left hand. So line up your thumb in the direction of the velocity vector, fingers along the direction of the magnetic field. The palm is going to open up in the direction of the magnetic force. So the positive charge is moving in this direction across the magnetic field from left to right. So using the right-hand rule, line up your thumb along the direction of the velocity vector, the fingers along the direction of the magnetic field. Palm is going to face in the direction of the magnetic force. All right, so the strength of the magnetic force is going to depend on the angle between the velocity vector and the magnetic field vector. All right, so two-dimensional representation of three-dimensional vectors. The vector is coming out of the page, going into the page. Here's a uniform magnetic field region. Magnetic field is pointing into the page, and then you got the charged particle moving in the downward direction. Using the right-hand rule, number one, you can figure out the location of this charged particle at any given point in time. So what's going to happen is it's just going to go into circular motion. So it's going to get deflected to go in a circular motion. So what that means is the charged particles going across the magnetic field is going to wrap themselves around the magnetic field. In essence, that's how the Earth's magnetic field protects us from charged particles coming from space. Right, so they get deflected, they wrap themselves around the magnetic field, and they are driven into the atmosphere at the north as well as the south. All right, so the magnetic force is a vector cross product. So it's the velocity across the magnetic field is going to give you the direction of the magnetic field. So that's the equation we use for that purpose. All right, so all right, problem number 2 is the one that I want you guys to focus on as you're getting ready for the test. There are 3 problems that I'm going to identify. Problem number 2, make sure that you know how to do this problem. All right, so go back to the lecture video and then look at the way it is done. All right, so there's going to be an accelerator. The particle is going to be shot into a constant magnetic field region. Accelerator is your capacitor. And then once it's shot into a constant magnetic field region, it's going to go into circular motion. So it's going to have a radius, it's going to have a speed, this and that. Make sure that you know how to do this problem. All right, so I'm not going to go over this problem here. Obviously, just go back to the lecture video and make sure that you guys know how to do that. Right, so that's one of the problems to focus on. All right, so here's a current wire inside a constant magnetic field. The current is going up. There's a deflection to the right. Current is going down. There's a deflection to the left. So wire is going to get deflected depending upon the direction of the current. So the question becomes, what's causing the deflection? What's causing the deflection is, once again, the magnetic force. All right, so the current implies that charges are moving in this direction inside a magnetic field, and the charges are moving across the magnetic field. Any charge going across the magnetic field is going to experience a force of deflection. It's going to experience a magnetic force. All right, so this formula is going to get transformed into this formula right there. All right, so this is the same as the right-hand rule number 1, except this is for a current. So the current is moving in this direction along the length of the wire. So L indicates the direction of the current. The vector L indicates the direction of the current. And so B is a vector. So once again, you end up getting a cross product. All right, so this is the right-hand rule number 1 for the current, or for a current inside a wire. All right, so and then the next concept is what happens to a loop, a wire inside an external magnetic field. What's going to happen to the loop of wire is it's going to try to line up its area vector in the direction of the external magnet. All right, so the current going up in the upward direction is going to experience a force in this direction. All right, so it's going to experience a force in this direction. Into the page, current going down is going to experience a force in this direction. Eventually, this thing is going to spin to line itself up, to line its area up in the direction of the external magnetic field. All right, so instead of saying it that way, instead of saying, oh, it's going to try to line up its area vector in the direction of the external magnetic field, we'll say it's going to experience a torque, which means that it's going to spin or twist in order to line its magnetic dipole moment up in the direction of the external magnetic field. All right, so the magnetic dipole moment tells you something about the magnetic strength of this loop and the direction of that magnetic strength. All right, so the direction of the magnetic dipole moment. So it depends on number of turns that you have, and depends on the amount of current in each turn, and depends on the size of the area of the area in the middle. All right, so if the magnetic dipole moment is not lined up in the direction of the external magnetic field, the loop is going to experience a torque to line itself up, to line up the magnetic dipole moment in the direction of the external magnetic field. So, and this is the formula we use for that. All right, so here's the cross product of this formula, and here's the scalar form of it. All right, so that's pretty much it from chapter number 29.
Is the same as the force between two current-carrying wires.
All right, so what's causing the attraction of these wires in this scenario? All right, so you should be able to explain that sort of stuff. So Ørsted discovers
Hans Christian Ørsted.
that the current causes magnetism, right? All right, so you can figure out the direction of the magnetic field, once again, using your right hand. So this becomes the right-hand rule number 2. Line up your thumb in the direction of the current, the fingers will curl in the direction of the magnetic field. So the question becomes, how do you mathematically model this? All right. So there are 2 ways of doing it. One of them is the standard method of using the Biot-Schwarz law. That's mathematically complicated, so it's really not worth our time. The second way of doing it is the Ampere's law. All right. Either way, people will come up with this formula. All right. So a bunch of formulas that I want you to be able to identify. As soon as you see the formula, I want you to be able to visualize this. All right. Once again, a million times I'm saying this, guys. The formulas they represent something, either visualizable or it's something which is extremely abstract. All right. Either way, you have a visual picture in your head that you can put on paper at some point. This is a straight wire. There's a current within, and this gives you the strength of the magnetic field at any radial distance away from the wire. All right. So the further away you are from the wire, weaker the magnetic field is going to be. All right. Now this is a loop of wire, and you're interested in the strength of the magnetic field in the middle. All right. So if that's the case, you cannot use this formula. Instead, you will get to use a formula which is going to look like this, except pi is going to be missing. All right. So this is going to give the strength of the magnetic field in the middle of a loop a wire. All right, so this is the total magnetic field, strength of the magnetic field right at the middle. So instead of a single loop, you may have multiple loops. If you have multiple loops, that's known as the solenoid. This is the length of the solenoid. All right, and capital N is going to represent the number of turns that the solenoid has. So the strength of the magnetic field within is represented. All right, so the current is going to cause magnetism, and there's a formula. The formula is this. All right, so N, lowercase n, is going to represent the total number of turns per unit length. Mu naught is your constant, and this is the current. And now, once again, you need to have a really good understanding of what this formula represents. What this formula represents is the strength of the magnetic field inside the solenoid, not outside, inside the solenoid. In fact, it represents the strength of the magnetic field in a very small region inside the solenoid where the strength of the magnetic field is constant. That's what it means. So that's your solenoid. All right, so this is for a straight wire. This is for a loop of wire. And this formula is for a solenoid, the strength of the magnetic field. All right, so know how to use the Ampere's laws and know how to use them properly. All right, so it's kind of like the Gauss's law, except this is for the magnetic field. All right, so this formula allows you to figure out the strength of the magnetic field around the loop. All right, so which means that you will have to traverse the loop in the counterclockwise direction. So the strength of the magnetic field is going to depend on the net current within. All right, so the current coming out, if it's coming out of the page, it's going to be positive. If it's pulling into the page, it's going to be negative. All right, so that's the Ampere's law. All right, so the Ampere's law, straightforward. So within this region, you got two current elements, and you are interested in the total magnetic field along the direction of the Amperean loop. So you're going to traverse the loop in this direction. So the total magnetic field along the direction of the loop is going to depend on the net current within. If the current is coming out of the page, it's going to be positive. If it's going into the page, it's going to be negative. All right, so strength of this magnetic field is going to be dependent upon the net current within. So this current is going to have a contribution. So is this one. This current is not going to have a contribution to the strength of the magnetic field. All right, so let's use this Amperean loop to figure out the strength of the magnetic field due to a single straight wire. All right, so you guys have to kind of practice something like this. This is straightforward. It's an easy way of solving these sort of problems. All right, so figure out the strength of the magnetic field at this radial distance away from this wire that you're looking at. All right, the wire is at the center. All right, just capital R, the region, just ignore that. All right, so I was going to do something else with it. I just forgot to delete it. All right. So this magnetic field is going to be due to this current element within. There's only one single current element within. Magnetic field is on the direction of the displacement vector in each and every single direction. So cosine of the angle is going to be 0. All right, so the vector expression is reduced to a scalar expression. So ds represents the total length of this curvature that you're looking at. That is the circumference of a circle. So it's going to be 2 pi r. This should be lowercase r, right? And then solve for b, and when you solve for b, we end up getting this formula for the strength of magnetic field around a straight current wire. All right, so that's it. Okay, the reason why you need to
is the same as the force between two current carrying wires.
All right, so what's causing the appearance of attraction of these wires? It so happens that the currents are in the same direction. The magnetic forces are going to be pointing towards each other. All right, so the magnetic force acting on this wire is going to cause a deflection to the right. The magnetic force acting on the other wire is going to cause a deflection to the left. If the currents are moving in the opposite directions, the wires will appear to be repulsed from each other because the magnetic forces on each wire is going to be moving away from the other. So that's what we end up getting. All right, so the question is, how do you explain this? All right, so the magnetic field generated by the first current acting on the second current wire is pointing in the opposite direction. The current is moving in this direction, so using the right-hand rule number 1 for the current, you will notice that the force causing the deflection is going to be pointing towards the other one. All right, so this is the magnetic force that you're looking at. Likewise, when the currents are moving in opposite directions, this time the magnetic field generated by the first current is going to be pointing in the opposite direction just like before, except the current changed direction. So using the right-hand rule number 1 applied to the current, you will notice that the force is pointing in the opposite direction. So these wires are going to be repelling each other in that sense. All right, and my recommendation is know how to do the derivation for this. All right, so this is your second problem that you need to focus on. All right, so here's the magnetic field acting on the second current due to that first current loop. All right, so this is the magnetic field generated by this current. Current is coming out of the page, right, in this case. So because the current is coming out of the page, it's going to experience a magnetic force to the left, and the magnetic force to the left is given by this formula. And then obviously you need to know how to adjust the formula. So B is the magnetic field acting on this wire, so it's going to be B1. I is going to be I2. L represents the length of the wire. The angle is between the direction of the wire is coming out of the page, and the magnetic field. So wire is pointing out of the page, and the magnetic field is in the opposite direction. So the angle is going to be 90 degrees. So sine of 90 is going to be 1. And immediately you come up with a formula that represents the magnetic force. All right, so that's it. You can repeat the same thing to figure out the strength of the magnetic force acting on the first current wire. And it's going to look the same, except the formula, the subscript is going to be different. All right, so practice that one. All right, here's the third thing that you need to focus on. The strength of the magnetic field within and as well as the outside of a current wire when there's current running inside. All right, so this is the thickness of the wire, capital R. All right, so let's figure out the strength of the magnetic field right at the surface. All right, this time we're using the Ampere's law. All right, so the magnetic field and the displacement vectors will be pointing in the same directions, each and every single point along the curve. So the angle is going to be 0, cosine of 0 is going to be 1. All right, so vector expression is reduced to scalar expression. All right, so the total length of the curvature is the same as the circumference of the wire. So it's going to be 2 pi r in this case. So the expression is reduced to this. So that's the strength of the magnetic field right at the surface, at the perimeter of the wire. All right, so what is the strength of the magnetic field inside the wire? All right, so you draw out your Amperian loop, but then it's supposed to be a circle. So the strength of the magnetic field is going to depend on the net current within. So I prime represents the net current within the loop. All right, and so once again, this represents the circumference of the Amperian loop under the circumstances. Now, for us to be able to interpret this formula, we need to be able to express the net current within in terms of net current within the loop, Amperian loop in terms of the net current inside the wire. And for us to be able to do that, we have to make the assumption that the current density inside the wire is constant. All right, so if the current density inside the wire is constant, then we can come up with an expression for the amount of current inside the Amperian loop versus the amount of current inside the wire. All right, so this I prime is the amount of current inside the Amperian loop, and this is the amount of current inside the wire. So you isolate I prime and then just plug it back into the formula that we came up with. And then you simplify it. The only variable on the right-hand side is the lowercase r. So this is the variable radius. So the radius is going to change from the center all the way up to the perimeter of the wire. So as this so happens, what's happening is as you start to increase the radius all the way up to the perimeter of the wire, the strength of the magnetic field is increasing. So all the way up to the perimeter, the strength of the magnetic field is going to increase, and once you're outside, it's going to diminish inversely. Is the radial distance changes? All right, so inside the wire, inside the radius of the wire, the strength of the magnetic field is going to increase radially all the way up to the perimeter. And then once you're outside, it's going to diminish inversely as the radial distance. All right, so that's it. So the strength of the magnetic field increases all the way up to the perimeter, and then once you're outside, it's going to diminish radially. All right, so the couple of things to talk about from a conceptual perspective. All right, so this is your solenoid. This formula is going to give you the strength of the magnetic field within only with this small region that you're looking at. All right, so that's your solenoid. And then there's a derivation involved that I'm not interested in. Okay, so the same derivation. All right, so the formula just gives you the strength of the magnetic field only within this region. All right, because the derivation is done based on an assumption that this solenoid is infinitely long, and there's no such thing, obviously. If you take a solenoid and then turn it into a donut, it becomes a toroid. All right, so the strength of the magnetic field inside a solenoid is going to be constant. The strength of the magnetic field inside a toroid is not going to be constant. All right, so strength of the magnetic field inside a toroid is going to depend on the radial distance. All right, so smaller the radial distance is. All right, I'm just muting everyone. All right, smaller the radial distance is, the stronger the magnetic field is going to be, which means that magnetic field within closer to the inside perimeter is going to be stronger. And as you start to move towards the outer edge, it's going to get weaker. All right, so what's the explanation for that? The explanation for that is the strength of the magnetic field is going to depend on the number of turns per unit length, despite the fact that the number of turns within the inside perimeter is the same as the number of turns inside outside perimeter, right? So the number of turns in the inside perimeter is the same as the number of turns on the outside perimeter. The number of turns per unit length is going to be larger on the inside perimeter because the length of the perimeter, the circumference of the perimeter, is smaller on the inside than on the outside. All right, so which means that the current is going to have a much bigger contribution to the magnetic field on the inside. That's what I mean. All right, so the toroid is going to have the same formula. Get to the same formula. All right, so here's your toroid. So the strength of the magnetic field closer to the inner parameter is going to be stronger than the one which is outside parameter. All right, so the derivation itself is not that important, but the final interpretation is. All right, so the strength of the magnetic field within is going to be represented by this. So these are the total number of turns divided by the circumference of the loop. The inner loop is going to have a small radius. The outer loop is going to have a larger radius. Despite the fact that the formulas look the same between the toroid and the solenoid, and here is going to be sensitive to the radius because the unit length depends on the circumference under the circumstances. So this becomes the formula.